Have you ever really stopped to think about how an email gets from you to someone on the other side of the planet in, like, the blink of an eye? It's one of those things we take for granted, but it's an absolute modern marvel. So that's what we're going to do today. We are going to follow the incredible high-speed journey of one single packet of data. I mean, it really does feel like magic, right? But what's happening behind the scenes isn't magic at all. It's this incredibly logical step-by-step process. So we're going to trace the exact path that one tiny packet takes as it zips across the vast highways of the internet. Let's start right at the beginning, on your local network.
All right, so the very first part of our packet's journey is actually a really short one. It all happens right there, inside your local network. You know, your home Wi-Fi, the office network, whatever. Before this packet can even dream about hitting the open internet, it has to find the right door to leave through.
Now, every single device on a network has two different kinds of addresses. First, you've got the IP address. Think of that like the mailing address on a letter. It tells the global system what building to deliver it to. But then you have the MAC address. That's more like the person's name on the letter. For that very first local handoff, you don't just need the address of the building, you need to know exactly who you're handing the packet to.
And that brings us to the first big puzzle our packet has to solve. See, your computer knows the destination IP address, the where. But to make that first jump, it needs a physical MAC address, the who. So how does it connect the dots?
Well, it uses this clever little process called ARP resolution, which is basically a digital roll call. Your computer literally broadcasts the message to every other device on the local network, shouting, "Hey, who here has this IP address?" The one device that has it raises its hand and says, "That's me, and here's my MAC address." Then your computer scribbles that down in a little digital notebook called an ARP table, so it doesn't have to ask again for a little while.
And that, in a nutshell, is the Address Resolution Protocol, or ARP. It's the critical link between the logical world of IP addresses and the physical hardware world of MAC addresses. Without it, our packet couldn't even take its very first step.
Okay, so our packet has used ARP to find the MAC address of its first destination, the gateway router. It is now time to leave the cozy local neighborhood and head out onto the wild, vast expanse of the internet.
Your router is, for all intents and purposes, the post office for your local network. It sits right at the edge, collects all the outgoing mail, all those packets, and then it figures out the best way to send them on their way. It's the gatekeeper between your private network and the public internet.
So how does the router know where to send everything? Well, it looks at its routing table, which is kind of like a digital map or a train schedule. It checks the packet's destination IP and finds the best route. The table tells it the next hop, the very next router to send it to, and even estimates how many hops or jumps it might take to get there. And see that default route at the bottom? That's the catch-all. If the router has no idea where the destination is, it just follows that rule, which is basically the just send it out to the wider internet and let someone else figure it out.
And just like that, our packet has left the building. It's been handed off by the local router, and it is now officially on the internet, zipping across this massive interconnected web of networks, hopping from router to router at pretty much the speed of light. Here's the key thing to remember. The internet isn't just one single entity. It's actually a gigantic collection of separate, independent networks called autonomous systems. These are run by internet service providers, big universities, giant tech companies, you name it. And the special language they all use to talk to each other and trade traffic information? That's called BGP, the Border Gateway Protocol. It's literally the glue that holds the entire global internet together. Okay, but with millions of routers all constantly updating their maps, what's to stop things from going wrong? What if two routers get confused and just start sending a packet back and forth to each other forever? How do you prevent those kinds of infinite traffic jams? The solution is this brilliant little feature inside the packet's header called Time to Live, or TTL. The best way to think of it is as a countdown timer, or maybe a bus pass with a limited number of rides. Our packet starts its journey with a set number, let's say 8 for this example. At the very first router it crosses, that number gets knocked down by 1. So now it's at 7. After the next hop, bam, it's down to 6, and this keeps happening at every single router. Now, if this countdown ever hits 0, the router that gets it knows something is wrong. It knows the packet has been wandering around for way too long, so it just discards it, preventing it from looping forever and clogging up the network. It's a really simple but totally genius fail-safe. So after hopping across who knows how many routers, our packet finally arrives at the gateway router of its destination network. It's made it to the right city, now it just has to find the right street and knock on the right door. This is the last mile of its journey.
Now, big organizations, they can't just plug thousands of computers into one giant network.
That would be absolute chaos. So what they do is use a technique called subnetting. It basically lets them take their huge block of IP addresses and chop it up into smaller, much more manageable subnetworks, like one for the engineering department, one for sales, and so on.
An IP address really has two parts. You've got the network ID, which acts like a zip code. It gets the packet to the correct neighborhood or subnet. And once it's in the right neighborhood, the host ID takes over. That's like the specific street address that pinpoints the exact computer it needs to go to. So how does a router know which part of the address is the zip code and which part is the street address? It uses something called a subnet mask. You can think of this mask as a stencil or a filter. By laying it over the IP address, the router can instantly figure out which part is the network part and decide, hey, is this packet for someone on my local block or do I need to forward it somewhere else?
So far, we've followed the packet's path, but we haven't actually looked inside the packet itself. Let's zoom in and take a look at the information it's been carrying this whole time that makes this whole incredible trip possible.
The IP header is basically the shipping label on a package. It's got all the critical info, where it came from, where it's going, that TTL countdown we just talked about, a little note about what kind of data is inside the box, and a checksum, which is a clever way to make sure none of this information got garbled or corrupted along the way. And this brings us to a really key concept, encapsulation. The easiest way to think about it is like Russian nesting dolls. The actual data you want to send, that's the smallest doll. It gets put inside a TCP or UDP wrapper. Then that whole thing gets put inside the IP packet for its global journey. And then that entire packet gets put inside an Ethernet frame for the local, physical delivery at each step. Each layer just adds its own wrapper to do its specific job.
So let's just do a super quick recap of this incredible journey. Our packet started with an ARP request just to find the local gateway. Then it hopped across the entire globe, guided by routing tables and BGP, while its TTL countdown kept it from getting lost. And finally, a subnet mask helped it find the exact computer on the destination network. And the most amazing part? This all happened in a tiny fraction of a second. It's absolutely mind-blowing.
And that really brings us to a final, pretty big thought. The core principles that make all of this work, IP addressing, routing, ARP, these were designed way back in the 1970s for a tiny little network connecting a few universities. And today, it underpins our entire global society. So the really big question is, as we start connecting billions, maybe tens of billions more devices with the Internet of Things, how is this foundational architecture going to have to change and evolve to handle the future?